welcome back for some more structural engineering. Today we're going to have a look at frames, specifically a beam column, meaning that we have one vertical member and one horizontal member. Let's see how we use all the things we learned before about solving reactions and figuring out internal forces to utilize in this structure. Let's get to it, shall we? As you can see here, we have this structure, ABC, that's the column, that's our vertical member, and CD gives us that beam member. And they're attached rigidly, so they form a beam column, a type of frame. We can see here that at A, we have a pin support, and at D, we have a roller support. We have to start off by drawing a free body diagram and finding those reactions. So what I'm going to do first, I'm going to replace that pin support at A with two forces, AY and AX, and at D, I am going to replace that roller support with a reaction force of dx. Now, note, unlike a lot of the beam cases that we've solved, that actually in this case, we've got two forces in the x direction and only one in y. And we'll see how that influences how we find reactions in just a minute. Let's start off by finding our reactions. I'm going to start off by the sum of forces in x equals 0, with this being my positive direction. So I need to collect everything in x. So I've got ax in the positive x plus dx in the positive x, and I've also got that 5 kilonewtons at B also in the positive x direction, so plus 5 equals 0. I can't solve it, as you can see in this case, because I've got two unknowns, ax and dx, but I can say that the relationship is ax plus dx equals minus 5. And I'm just going to save that for when I have a bit more knowledge about the relationships between the reactions. Moving on now to the sum of forces in the y direction equals 0, with this being my positive direction. I've got a reaction of AY in the positive direction, and the only other thing that I have is that uniformly distributed load along CD of 2 kilonewton per meters. It's going in the negative y direction, so minus, and I have there 2 kilonewton per meters over 5 meters. So as we said before, the area of that load, so if this is my load, the height is the value of the load, so 2 kilonewton per meter, and the length is 5. The area of this is the force, so minus 2 kilonewton per meter times 5 meters equals 0. I can see here the meter from the 2 and the meter from the 5 cancel each other out, and therefore I'm left with AY equals 10 kilonewtons. And the last thing that I want to do is sum of moments. I am going to do sum of moments around A, and this is the positive direction according to my sign convention. Starting off at D, I've got the reaction force at D, contributing a negative moment, so minus dx. The force is in the x direction, so the perpendicular distance is going to be along y, and I can see that from D to A, the distance in y is 6 meters, so times 6. I've also got that distributed load, that also contributes a negative moment, so minus the force, that is 2 times 5, as we've discussed before, that is the force, and the distance is going to be in x. So really the distance is going to be from where that resultant force would be, which would be in the middle of the 5, and the distance along x to A is 2.5 meters. So times 2.5, and that there is the distance. I've also got the force of 5 kilonewtons at B, also contributing a negative moment, minus 5. The force is in x, the distance has to be in y. The distance between B and A in the y direction is 3, so minus 5 times 3. And that's all I have, so that needs to equal 0. That gives me 6 dx equals minus 40. And if I divide everything by 6, I get that dx equals minus 6.67 kilonewtons. And now I can finally go back into this first equation and find what ax is. So ax, as we said, is going to be minus 5 minus dx, and that is minus 5 minus 6.67, and so if I solve that, I will get here plus 1.67 kilonewtons, and that is ax. And now the very last thing that I want to do is I want to replace ax, ay, and dx in my graph with the actual directions and values of those reactions. So that will be my final step to solving the reactions. So dx we said was minus, that means I assumed the wrong direction. In reality, dx is in this direction and it is 6.67 kilonewtons. Ay is in the direction I assumed, so that direction is correct and it is 10 kilonewtons. And ax worked out as positive as well, so that is the correct direction, and it is 1.67 kilonewtons. I can do a check at this point, for example, moments around D, moments around C, really moments around any point, just to check that it all equates to 0, and that way I can verify that my reactions are correct. So now we have the reactions, and that is the first stage to solving this. Now, as we saw, finding the reactions is exactly as we found the reactions many times before, and the only difference now will be in finding the internal forces. And to be honest, the main difference here is just that when we have horizontal members, like we did in beams, we have axial force in the x direction and we have shear force in the vertical direction, and that'll change between the column and the beam, and we'll see that now. But all in all, we have exactly the tools that we need in order to solve this. Let's see together, shall we? I'm just going back to my free body diagram with those reaction forces drawn in, and you can see here that at the bottom I've already put some frames to capture the axial load, the shear load, and the bending moment diagrams. Now, usually I tend to do these along the way as I'm solving. That way, when I solve different sections of the frame, I don't have to at the end try and remember what I was doing and go back. I'll do it as I go along. We're going to start off with the column, with the vertical part of this frame. Now I can see that there is a change in B, right? There's that additional force. So generally what we want to do is we always want to look at sections without change and create different sections after change. So the best places to look in this diagram would be to make a cut somewhere between A and B before that 5 kilonewton appears, to make a cut somewhere along B and C after that 5 kilonewton appears, and then to make a cut somewhere between C and D to see what the influence of that uniformly distributed load is. Let's begin with section AB, okay? And I'm going from A to B. The first thing I'm going to do is I'm just going to draw it out. So if I look at section AB and I've cut somewhere between A and B, I don't have those 5 kilonewtons yet. What I do have is I've got this reaction force of 10, I've got this reaction force of 1.67, I have the internal forces that I expose the minute that I make the cut. Because obviously the minute I cut this column, the external forces have to balance those external forces. So let's draw them in. Axial force will always be normal to the element. My shear force will always be perpendicular to the element. And I'm going to draw my bending moment in as well in the positive direction. Now note that in this case, I've said that they all are potentially a function of y. And that is because I have cut this and my element is now going in this direction, right? I'm moving here. So I'm moving in this y direction. And y is between 0 and 3 meters, right? We're going just up until point B, just up until the influence of that 5 kilonewtons. So now that I have this drawing, it is really not that difficult. What I need to do is once again look at equilibrium. So look at 3 equations of equilibrium and solve them. Let's start off with the x direction. So sum of forces in x equals 0. And here in x, I've got S, the shear force, which is potentially a function of y, in the positive x direction, plus 1.67, also in the positive direction, equals 0. I can see actually that this is going to be a constant. So the shear force is going to be minus 1.67 kilonewtons constant. Now, I think the interesting thing to note here probably is that when I was looking at beams, normally beams tend to be along the x-axis, which means that normally I would get axial force along the x-axis, which is not the case here. So that is the interesting things about frames, how the shear and the axial force, they are x and y depending on if I'm looking at a column or looking at a beam or looking at a horizontal element or looking at a vertical element. Moving on now to do sum of forces in the y direction. And in the y direction, I've got the axial force plus 10, nothing else, so that equals 0. So I can see here that the axial force is also constant, and it is a compression force of 10 kilonewtons. And I've now reached the very last thing that I need to do. I need to do sum of moments, and I'm doing this along the cut. So where I've cut it, where I've exposed those internal forces. And that's just really because whenever I do moments, at the point that I'm doing the moments, the forces passing through that point cannot contribute to moment. And therefore, if I've made a mistake, say in the shear force or in the axial force, they're not going to contribute to the equations. So let's see what does contribute. I've got obviously that moment that I need to find, my, that internal moment that I've just exposed. The S and N pass through that point. The 10 also passes through the point that I'm looking at, right? This point here. And so the only thing contributing to moment is that 1.67, which is contributing a positive moment, so plus 1.67 times y, right? That depends on the distance. If my cut has been done at 1 meter, 2 meters, or exactly at B, that equals 0. So my equals minus 1.67y. I'm interested in 2 points really. What happens at A, what happens at B, or what happens when y equals 0, and what happens when y equals 3. Now there'll be cases where I'll probably be interested in different things along the way, say if I've been asked what happens between A and B, but in this case I just want to draw my graph. So at 0 I get a moment of 0, which makes absolute sense because there is no moment at A, we don't start off with a moment. And when y equals 3 I get minus 5 kilonewton meters. And now I have all the information that I need to be able to fill that first bit of each of these graphs. Let's start off with a moment actually. And that is because the moment, as we know, needs to be drawn on the tension side. So what side is that for me now? Now let's just see. I assumed that my moment went like this. I got a minus, which means that it doesn't go like that. My moment is actually like this. And the tension side is going to be this side because we can see that arrow is pulling up here, so creating tension on this side, and pushing down on this side, which means creating compression on that side. And that is the indication of how to draw the moment. I also know that it's going to be a straight line because I only have concentrated loads. When I have UDLs, I get a parabola. But you can see here that my equation here, right, is a function of y. Okay, so I know that is going to be a straight line. Let's just say this is 5, and that's my first one. That's a straight line, and this is 5 kilonewton meters. For S, I got minus 1.67, and for N, I got 10. And that is the first section complete. Let's now move on to section BC. I'm going to start off once again by drawing. Now I am actually going to draw it from A. So I'm going to add in these two reaction forces, 10 and 1.67. I'm also going to add that external load of 5. And I'm going to say that I'm going to cover this distance of 3. And then from here on, I'm at y2. Okay, so I'm going to cut somewhere in the y direction between B and C. And once again, expose my internal forces, which means that once again, I get N, this time potentially a function of y2. I get S, potentially a function of y2. And I've got my moment here, again, potentially a function of y2. And y2 is between 0 and 3 once again. So I've passed those first 3 meters, and then I have another 3 meters to pass before I get to C. All right, so let's see what that means for our internal forces. We'll start off by doing the sum of forces in x equals 0. So I've got S, function of y2, plus 1.67 plus 5. Okay, so there's a change here, equals 0, and that gives me a constant again, so not really a function of y2, minus 6.67 kilonewtons. All right, great, that was easy to start off with. Okay, let's now look at finding the sum of forces in the y direction, and here I've got the axial force, N, perhaps a function of y2, plus 10, and that's it, equals 0. So I find here that N actually is a constant of minus 10, And I can see that that is exactly the same as I had before, so not a change in the axial force. And that makes sense, right? Because I haven't had any change of forces in the y direction or in the axial direction. Moving on to the last thing, which is the sum of moments at the cut. So here I need to find that internal moment that I've exposed. So is it positive moment, my2? And here I've got a positive moment from the 1.67. Only this time the distance is 3 plus y2. And I've also got a positive moment from that 5 kilonewtons at point B, so 5 times y2 equals 0. If I reorganize that, I get that the moment equals minus 1.67, 3 plus y2 minus 5y2, and slight further reorganization gives me minus 5 minus 6.67 y2. 2 points that I want to find here. What happens when y2 equals 0? So that's exactly point B. And what happens when y2 equals 3? So that I'm at point C. When y2 equals 0, I get minus 5 kilonewton meters, which is exactly what I got before. Because there's been no jump in moment, there's no reason for the moment to change. That's great. And when I get to 3 meters, I get here minus 25 kilonewton meters. Let's start with a moment, put it on the graph, and that's us finished the column. So I can see here on the graph that now I'm going up to 25. You can see that we start in the same place. It's a straight line because they're only point loads, but there is a change in the angle. In terms of the shear force, the value's changed, but it's still a constant, and only this time it is minus 6.67, and my axial force has actually not changed, so I'm just still continuing here with a compression force of 10. And that's the column done. We can now move on to part CD, or the beam bit of the frame. But before we do, I do want to address that change from a column to a beam, or from a vertical member to a horizontal member. Let's do that by just looking at the column. And here there are all these external forces. Then I move on to the corner, and then from the corner on to this vertical bit, where once again there are all these external forces that I'm not going to draw. Now, when we looked at the column part, right, we had a force in this direction, a force in this direction, and a moment in this direction. Now, this is internal, and that means when I make these cuts, I need forces of equal value but opposite direction on the other side of the cut, right? Because when I put this all back together, these have to disappear. Now, these internal forces on the column are balanced out by, all these internal forces here. But on this corner, I need to balance it out by the internal forces on the other side of the corner, which means that on the other side of the corner, here I need a force in this direction, I need a force in this direction, and I need a moment in this direction for this to balance out. That in turn means that on the other side of the beam, when I want to kind of look at this bit here, this also has to close up to 0. So that means that here, in order for everything to be in equilibrium, I need to have the same values in opposite direction. So I need a force like that, a force like that, and a moment in this direction, okay? Because remember, all these are internal forces. I close up the cuts, they must disappear. Right? They're not external. I can't see them. I haven't put them on the structure. So with that in mind, we're now going to look at this bit here, okay? And note how, for example, this force here, this blue force, which is axial force here, turns out to be a shear force for the beam, or in the same way how this shear force turns to be the axial force here, okay? So that is the interesting thing in frames moving from the columns to the beams, that the axial and the shear forces swap. All right, now that we've covered that, let's solve it. Now I can look at this two ways. I can go from C to D, meaning that I either need to take into account everything that I found from A to C and put them forces and moments at the end of the beam. I can look at the whole structure from A, B, C and partially into D, or I can do something slightly easier and just look at the beam, so with my X starting from here, meaning that I am looking from D to C. Now if I do it that way, I can just look at it as a new section and then just check if at the corner everything matches up to what I'm expecting. So doing it like that, I've got a force, reaction force here of 6.67. I've got this external UDL here of 2 kilonewton per meters. And now I've got my forces. I've got my axial force here, NX. I've got my shear force here, SX. And I've got the moment, MX, with X going between 0 and 5. The reason that I'm not doing any additional cuts is once that UDL starts, nothing else really changes in the beam. There's no need to do more than one cut here. So now that we've decided on that, let's get started. Sum of forces in X equals 0. If this is my positive X, I've got minus NX minus 6.67, nothing else in the X direction, so that equals 0, and NX equals minus 6.67 kilonewtons. Okay, now, no, interestingly enough, that the shear force here was 6.67. So I already, from looking at and analysing the corner, understand where that value came from. Looking now at the sum of forces in the Y direction equals 0, I've got minus SX and also that UDL minus 2 times X. And that is because we said the force is the area, X is this is 2, so it's going to be 2 times whatever the X is, and that equals 0, so S is minus 2x. And so interesting what happens when X equals 0, which is at D, and what happens when X equals 5, which is at C. So at 0, I get 0, which makes sense, right? If I'm just at point D, that shear force hasn't really kicked in yet, and at 5, I get minus 10 kilonewtons. Okay, so here the shear force really was a function of X going from 0 to minus 10. And the last thing that I need to look at is the moment. Obviously that's the moment at the cut, so sum of moment at the cut equals 0. And here I can see that what I've got is minus, just because of the way that I've drawn it, so minus mx. I can also see here that I've got minus the UDL, so minus 2 times x. That gives me the force, and the distance is going to be x over 2. So times x over 2, which is the distance. And that's all there is in terms of forces contributing to the moment. So that equals 0. And that means that the moment equals minus x squared. So once again, what happens when x equals 0 when I'm at point D, and when x equals 5 when I'm at point C? So at 0 I get 0, which makes sense. I'm at a roller support. There's no concentrated moment, so that's looking good. And when x equals 5, I get minus 25 kilonewton meters, which is exactly the same as the other side of the corner, which again is good news because there has been no jump in moment. No moment has been added between the corners. My only question is, what side do I draw this on? Here, I assumed that this was the moment. It's not the case. The moment is really in this direction, meaning tension at the top. And that makes absolute sense here. So these are the same, right? This was 25 and this is 25. And they're on the same side of the corner, which means that they are, just like we drew before, in equilibrium with each other. Now this is going to be parabolic. So it's going to look something like that. Just to differentiate, right, this was a straight line here, this is a parabola, this is also a straight line here. Straight lines here and here because these are concentrated loans, parabolic line here because this is a UDL. That's the moment done. Let's quickly fill in the other parts. In terms of our shear force, we went from 0 to minus 10. So I'll just draw that in. That's a straight line, right? Because that was just a function of x. So here I've got 10. And in terms of my axial load, I had minus 6.67. So it'll be something like that, minus, and this is 6.67. Let's just have a look at these in a little bit more detail. Okay, I can see here parabola, as we discussed before, where I've got a UDL, and straight lines where I have point loads. I can see that the value of 25 and 25 is the same. They're also on the same side of the corner, so they're in equilibrium. And here I can see that that 10 is the same as this 10, okay, which means that the axial and shear force have swapped sides really. And again, this 6.67 and this 6.67. So what was the shear direction has become the axial direction, and what was the axial direction has become the shear direction. Also here, straight line, because we are just a function of x, UDL, function of x for our shear, and a function of x squared for our moment. And that's it. We've taken something that seems much more complicated than the things we've done up to now, because there have been elements in vertical directions and elements in the horizontal direction, a beam and a column. And we've managed to solve the internal forces for that as well. And I think that means we can practically solve anything that is in static equilibrium. That means that we only need the equations of equilibrium to solve. But join me again as we add more forces, more elements, and see what we can solve. Bye for now.